Okay, so the first thing is about the midterm. So I think last time I mentioned already that the midterm will cover the first 3 chapters, right? So the partial differentiation, the multiple integrals, and the vector calculus. Okay, so okay, so closed book and closed notes. Okay, so and this is the date and time which I have announced already at the beginning of the chapter, in the beginning of the semester, and the formula. So I will give the following formulas to you. Okay, if the problems require you to use them. Okay, so these are the formula that may be provided. Right, so it depends on the question. So I will upload this document to the Blackboard today. Okay. Are there any questions about the midterm? Okay, so if not, we'll continue chapter 4. Okay, so the ODE. Okay, so first I will talk a little bit on a method that we will use to solve a specific type of differential equation, and then you'll go work on one tutorial problem. Okay, and then after that I will talk more, and then you work on the second one. Okay, depend on how much time we have today. Okay. Okay, so last time we have talked about 2 of the methods that we'll use to solve ODE, right? So including the so-called direct integration, which is really the trivial one, right? So basically just integrate both sides, and then you take away you undo the derivative, right? So and the second one, right, which is known as the separation of variables, right? So this is actually a very useful one. So now the other method that I'm going to talk about is this type, okay, which is known as the this method is for solving the so-called homogeneous equation. Okay. So I'll talk about this method, and then I'll give you one tutorial problem on that. Okay. So whenever we see the ODE of this form, okay, we call this the homogeneous equation. Okay, first of all, why is it called the homogeneous equation? Okay, so it is because the function on the right-hand side, okay, is a so-called homogeneous function. Okay, what is the definition of homogeneous function? Okay, so this is just a name, right? So but it's good that we know what it means, right? So for a function, right? So let me write down a function of, well, it can be a multiple variable function, but let's say if I have a function of 2 variables, okay, f(x) and y. So and it has the following properties, then we say that this is a homogeneous function. Okay, so if f ex and ty, so that is if we substitute ex and ty to this function, so that t is any number that you pick. Okay, so if you find that you put tx and ty, right, so input as the input of the function, and you get this. So if you put f tx ty, and it turns out that you find that it gives you t to the power n times fxy, then this is known as a homogeneous function of degree n. So again, so this is just really a name, a definition, right? So we are actually not too concerned about this, but now I just want to tell you why this one is a homogeneous function, right? So because, right, so I have this function. If I have a function that can be written as a function of y divided by x, so it means that this function, right? So this function is depending on both x and y, right? So but the terms always comes with this ratio. So that means, for example, let's say if I have this f equals, right, y divided by x squared, right? So if I have this f equals sine of y divided by x, right? So if I have this f equals e to the y divided by x, right? So all these functions, of course, well, it's a function of x and y, right? So we see that, but you can see that this function, right? So whenever we have x and y, but they always come together, right? So then that means this function, instead of just writing it as function of x and y, I just simply put it as function of, right? So y divided by x. So these are the examples of this function, right? So now, then the question is, so are these kind of functions homogeneous, right? So what you need to do? So basically, if I put, right, so for example, if I take this one, and now I put y to become ty and x become tx, right? So when you realize that t always cancel, right? So same thing for this one and this one. You put ty here and you put tx here, then just give you back y divided by x. Right? So t always cancel. So that means, right? So all these functions, so are homogeneous functions. Okay. So and can actually say that it's a homogeneous function of a degree 0, right? So and that's why, okay, that's why whenever you have a function of x and y, which can be in fact written as a function of y divided by x, then this one is a homogeneous function. Okay, and that's why this differential equation that involving this homogeneous function, okay, is called the homogeneous equation. Okay, so that's the reason. Okay, but regardless, okay, even we don't remember actually the definition of a homogeneous function, okay, just remember this form. Okay, whenever you see dy dx equals to a function of y divided by x, then that's the homogeneous equation. Okay, so last time I also mentioned that later we'll see another type of differential equation which we also call homogeneous equation. Okay, so but just a warning, okay, don't confuse the two. Okay. But anyway, so when we see this form, okay, so how do we solve it? Okay, so that so can we use the method that we learned previously? Can we use direct integration? Right, it's probably not, right? Because if you integrate the left hand side, you get y, but if you integrate the right hand side, right, so with respect to x, you cannot do that directly, right, before you actually know y, right? So can we do a separation of variables? Okay, so again, it depends, right? So if this function, for example, is let's say is just this, then in this case you see that, okay, dy dx equals to y squared divided by x squared. This one you can actually use separation of variables, right? So that's okay. But how about if you have a function that looks like this? Okay, so this time you realize that you cannot just make one side of the equation only contain x, but the other side of the equation only contain y. So for this case, okay, so type separation of variable won't work. And so here we are talking about another method. Okay. So the trick is actually to do a variable substitution. Okay, is that I let y equals vx. So v is a new variable. Okay, so v is not a constant. Okay, v is not a constant. V is a new variable. Okay, so well, at the end of the day, you may expect that v is actually also a function of x, right? So because we are solving for y as a function of x, right? So v is a new variable that we don't know about anything about it yet, right? So we just let this new variable, okay, so to be having this relation. So v equals to y divided by x. So essentially. So then now because of that, then this f of y divided by x becomes f of v. Right. And then on the left-hand side, so now I want to get rid of the y. Okay, I want the whole equations only contain v and x now. Okay, no y. Okay, so and then I just put this y equals vx into this differentiation symbol, right? So and then I use product rule for the left-hand side. So then I got x dv dx plus v equals f of v. Okay. So now we transform, right? So these equations that involve x and y to this differential equation, which involve x and v. Okay, so we get rid of the y. Okay, so now if we look at this, now we realize that we can use separation of variable. Okay, so because now we can really put all the terms, so depends on v, right? So on the right hand side, right? So I will have this dv dx equals f of v minus v, and that means that is dx divided by x equals dv divided by f of v minus v. So that's the trick, right? So using this substitution, right? So it allows us to transform this equation to a form that allows us to use separation of variable. Okay. So here I just write it down again. So now separation of variable is done, and then of course the next step, of course, just do integration. Okay, integration both sides, and then at the end, the right hand side, okay, is the exponential function of this integral. Okay. So there are a couple of things to remind you. Okay, so remember that when I integrate this dx divided by x, right? So it should be a log of absolute value of x, right? So here I drop that, and I just basically let this unknown constant to take care of the plus or minus sign. Okay, but now look at the right hand side, right? So if I do the integral, then I will get, after I do the integral, I will get a function expression that depends on v. Right? So x equals to this exponential of function of v. Right? So at the end, of course, if you can, right, so or you should, is that you want to go back to express this v, right, in terms of this y divided by x. Right? So then, because at the end, what we want to do when we say we solve this equation, right, we want to find the relation between y and x, right? So the v is just the variable that we make use of. But at the end, you want to put back your original variable back in. So then this is a trick, right? So whenever you use this form, then you use this substitution, okay, and then to make it to a form that you can do separation of variable. Again, the question, of course, is whether you can do this integral or not, right? And really, it really depends on the problem, right? So that one we don't know, right? So in fact, you may realize that in many cases, right? So this integral, right? So can be you might not be able to do it analytically, right? So for example, right? So even if you try this, even if the f is sine, right? So then you deal with sine of v minus v, then you can't do it analytically. Okay. So therefore, actually, this, okay, so this method, this substitution, okay, will work for only work for the cases where this integration is doable, right? So and that actually there are not that many cases. But anyway, let's try to actually do. Let me try to do an example here. Okay. Okay, so let me solve this. This is the simple one. Okay, so okay, so this for sure, as I mentioned, you know that this one you can solve it using separation of variable anyway. But here, just practice using the new substitution method. So let's try to do the substitution, right? So so what do we do? So let y equals dx, right? Then what you have is d dx, and then the right hand side is just v squared. So and then the left hand side is x dv dx, okay, plus v, right hand side v squared. Then you put everything to the right hand side. Right, so then now separation of variable. Right, so dx divided by x. Okay, so integrate both sides. So how do I integrate the one on the right hand side, right? So first, we want to make it decompose it into two partial fractions, right? So because notice that this, right? So v squared minus v inverse is this 1 divided by v times v minus 1, right? And this one is actually 1 divided by v minus 1 divided by v minus 1. So then we have this, right? So we know how to do this, right? So there's just give me log. So then I have this log. Okay, remember the absolute sign of x plus some constant c equals to log of v minus log of v minus 1, right? So in principle, on the right hand side, you also need a constant, but just one constant is enough, right? Anyway. Okay, so and then what you do next, right? So you take exponential for both sides. Okay. Running out of space. So let me put it here. So then I will have this x times this e to the c is another constant, right? So let me just call it c prime, and then equals to this. Right. And as I said, we are not done because we want to put the v back to y divided by x. So right. So because of the absolute sign, so in principle we need to consider cases, right? So whether the negative or positive, right? So but let's say if we just consider both to be positive, that case, then what you have is just this, and then eventually, right? So you can just put y as a subject and just and then find out the y as a function of x, right? Okay, so then okay, in this slide it's just another example. Okay, so I have all the steps shown here, but for the key here is that you need to identify, okay, so this one, whether this one it can be written as a function of y divided by x or not, right? So then you can actually see that it's actually quite obvious, right? Because this y divided by x square, right? So the second term is just, right? So 2 y divided by x. And then well, just following the same tricks, right? So doing this substitution. So I'm not going to walk through the whole thing again. But now let me have you to do one problem. Okay. So again, go to the tutorial file for today. So try to do not question 1, actually question 2. Question 2. So this one is actually a bit tricky than what I just shown you. Okay. So first of all, if you just look at this equation, okay, so it doesn't look like it can be written in terms of a function of y divided by x, right? Because if you divided the numerator and the denominator by x, right, so you realize that this will give you 3 divided by x and this 6 divided by x. Okay, so this one by itself, okay, it's not a homogeneous function yet. Okay, so then the first thing I just want you to think about it a little bit is that you first of all you need to make some variable substitution. Okay, so to make the equation or to make this function to look like a homogeneous function. Okay, so that's the first trick you need to do here. So what you want to do here is essentially if you get rid of the 3 and get rid of the 6, then we are done, right? So then we only have the 2x minus 5y and 2x plus 4y. Then you divide both numerator and denominator by x, then you realize it is a homogeneous function. But how do you get rid of the 3 and the 6? That's the thing. Okay, so the hint is that you let this x to be equals to a new variable which I call x1 plus some constant alpha, and then you let y to be equals to new variable y1 plus another constant beta. So then I want you to rewrite these equations, this differential equation, in terms of x1 and y1. Okay, such that, so you need to pick the value of alpha and beta such that, okay, so the whole equation, okay, after we expressing in terms of the new variables, does not have this constant term alone. We'll try to put these new variables in and see what alpha and what beta that we need to make this 3 and make this 6 goes away. So actually, even after you make this variable change, right? So the left-hand side, you don't need to do anything, right? So dy dx will be just the same as dy1 dx1. Okay, so if we make this variable change, right? So the right-hand side becomes this. So 2x1 plus alpha minus 5 y1 plus beta plus 3 divided by 2x1 plus alpha plus 4 y1 plus beta minus 6. So you want to get rid of the 3 and the 6, right? So then I have this 2x1 minus 5 y1, right? So and then plus 2 alpha minus 5 beta plus 3. And then for the denominator, right? So 2x1 plus 4y1 plus 2 alpha minus 4 beta minus 6. So then you require, right? So you require this one to be 0, right? And this one to be 0. So then you look for the alpha and beta, right? So 2 equations, 2 unknown. You will find that what you need is that alpha equals beta equals 1. So then with that, the ODE becomes, so dy1 dx1 equals, right? So 2x1 minus 5y1 x1 plus 4y1. Now you do the tricks that we learned, right? So now you let right? So y1 equals v x1. So then I guess I'll just skip up some steps, but what you realize is that this x1 dv dx1 would be equals to 2 minus 5v divided by 2 plus 4v minus v. So after that, right, so again, separation of variables. Okay. So on the left hand side, so let's say I just have and then on the right hand side, okay, so again, skips the steps, but I'll just tell you that after doing the factorization, okay, I will get this. Okay. Now, integrate both sides, right? So integrate this, and again, so with this, right? So you need to again use the technique of this partial fraction, right? So this one, you actually can get, you actually can decompose this one into two partial fractions. Okay, so it will be this. So and after you do this, and then you can integrate this term, then the final answers follows, right? After you go back and substitute the v back to y and y1 and x1, and then of course you have to further go back and substitute this x and y, right? But skips all the steps. But this is because what follows is just the standard, right? So this is some tedious algebra. Okay. Okay, so now let me see. Let's take a let's take a break for 10 minutes. Okay, because I'll just finish this homogeneous equation, and then we'll come back at 12:20. Okay. Okay, so let's continue. So far we have done 3 types, right? So of the methods for these 3 types of the ODE. Okay. And then the next one that we'll talk about is the so-called the exact differential. Okay. So before talking about that, so let me ask you this question here. Is that so this is a plot that I borrow from the first chapter. Okay, so what am I plotting here? So this is a function of 2 variables, right? So a curved surface, and then I have the contour lines. So remember how contour lines are defined, right? So just cut it right into many levels, right? So for particular z value, right? So you get one contour line. Right? So let me call. Okay, let me call this a function. Okay, a scalar function, right? So v, x, and y. Okay. So suppose I want you to find the equation of the contour line. Okay, the equation of the contour line. So in this case, which are all these circles, right? So and you know exactly the equation for this contour line. So for example, this one, right? So is Vxy equals a constant, right? So this line specifically, this line 800, for example, right? So this contour line is right. So Vxy equals 900, right? So many contour lines, but so then in general, right? So the form of the contour lines can be written as Vxy to be some constant c, right? So this is the formula, the equation for the contour line. So given that we know what Vxy is. So of course this is very easy, right? If I give you Vxy, then of course you know that the contour line, the general equation is Vxy equals c. That's all. Okay, the answer. So but now suppose if I don't tell you Vxy itself, okay, I only tell you. So now you don't know Vxy, but I only tell you partial V, partial x, and partial V, partial y. Suppose I only give you these two information. Okay, of course, it depends on what V is, but in general, partial V, partial x is also a function of x and y. Right, so let me call this mxy, and this to be nxy. Right, so I give you the form of mxy and the form of this nxy. Okay, so I don't directly tell you what V is, and then I want you to find, right? So I want you to find the contour lines equation. So then what you do here, of course, is that you will want to, from partial V, partial x, this m, right? So and from this partial V, partial y, and this n, to figure out V itself, right? So that's what you would do, right? So if you give you this, then you try to find V, and then after that, after you find V, then of course the contour line equation is just that V equals c. Then you're done. Okay. So this is also something you have learned, right? So to find V itself from this big M and this big N, right? So remember in the chapter 3, when we talk about the vector field, right? So I given the two these two components, right? So and then you go back and find the so-called what we call the potential function, right? So mathematically, okay, so this is also something that you have done, right? So now what I will give you, okay, is that suppose we are indeed, okay, so walking along a contour line, right? So then that means, let me see if, so let's say initially I'm at this point, okay, and then I move x and y a little bit, okay, such that I move to this point, okay, still on the same contour line. So in this case, right, so the change of my height is 0, right? So because I'm walking along this contour line. So in other words, if I walking along here, so then if I consider the total differential, so the dv, which is equals to the partial v partial x dx plus partial v partial y dy would be 0. Right. So, but the condition is that when you pick your dx and dy, right? So you need to be careful, right? So you need to pick, right? So for example, right? So this one as your dx and this as your dy. So that means the dx and dy has to satisfy a certain relation, right? Such that the change of your position, right, does not result in any change of this function value v. Okay. So that means in this case, right? So that means what is the requirement or what is the relation between the dx and dy, right? The relation of the relation between the dx and dy, right? So from here is that dy partial v partial y has to be equal to minus partial v partial x dx. Right, so that means dy dx has to be equal to minus partial v partial x divided by partial v partial y. Okay. So that is the requirement for this y. Okay. So to make sure that you go along a contour line, so y and x are not, you're not really treating them as independent variable anymore, right? So because you need to make sure that you go along this contour line. So then this dy dx, right? So it's given by the ratio of the two partial derivatives, right? So which is just the ratio of these two functions, right? So let me just write it as, right, minus capital M and then divided by this capital N. Okay. So then now if I look at this is an ODE now. Okay. So dy dx equals to this. Okay. So that means if I'm seeing a type of ODE that looks like this, right? So that looks like dy dx equals minus capital M divided by capital N, then you know that what you are really looking for is that the relation between y and x refer to this contour line curve. So now this is the type of the ODE that we are looking for. Is that if I see the ODE of this form, right? So this one, and which is just this one, right? So this one is from this one here. Then what we would do is that if we find that this M and this N are indeed the partial derivatives of some function v, x, and y, okay, then we know that the meaning of this ODE is finding the equation of the contour lines of this V function. Okay. So, but of course, okay, so when I give this ODE to you, right? So the M and N can be any function, right? So the M and N not necessarily refer to the partial derivatives of some function, right? So then first of all, you need to test whether this and this are indeed corresponding to the partial derivatives of a function V. Okay, so, but if not, then that means, so if not, then this is still an ODE, right? This is still an ODE, but the meaning is not to find a contour lines of this V function. Okay, but it's still an ODE. So then first of all, okay, so we want to test, okay, whether these two are indeed correspond to the partial derivatives. So because if it is, then we know how to solve. Okay. If it is not, then you need to use some other method. Okay. So and if this is satisfied, okay, so then this type of equation is what we call the exact differential. So because if this is you realize that if this M is indeed referring to the partial derivative of X, then this N is referring to the partial derivative of Y, then the solution to this ODE is this V function equals to C, right? So basically, this is what I'm putting here is essentially what I just mentioned in the in this slide. Okay. So then the thing is, remember how to test whether this M and this N refer to the partial derivatives of a function, right? So remember how do we test it? Okay. So it's the same idea as how we test whether a vector field is conservative, right? So because if M is indeed partial V partial X, and if N is indeed partial V partial Y, then these two functions will satisfy this equation. So why is it? So because this partial M partial Y is actually given by this second derivative, right? Partial square V partial Y partial X, and this partial N partial X is given by this partial square V partial X partial Y. Okay. This should look familiar to you, right? So because this is exactly what happened, chapter 3. And right, so we assume that the function is differentiable, right? So and all that, and that's why, right? So switching the order of the derivatives, well, doesn't matter, right? So it still gives you the same thing. So then that's it, right? So then basically 2 steps. So when you see an ODE of this form, okay, M and N, well, depends on the question, right? So you test whether this M correspond to the partial derivative of some function, the partial derivative of X, and then N correspond to the partial derivative of the same function with respect to Y. If it is, then you know that this is an exact differential, and then you will try to find the V itself, and then your answer, the solution of this equation, is that V is a constant, right? The solution is the contour line of that function. So right? So the procedure, right? So the procedure of finding the V, right, from M and N have also been discussed in chapter 3, right? So this slide actually is the exact same slides that you see in chapter 3. Okay, so might want to review that. So here, let's actually try to solve a problem. Okay, so I want you to solve. So actually, instead of directly saying this, let me say this, right? So I want you to solve this. Right. So this is the, let's say this is the question. Okay. I want you to solve this equation. Okay. This is the question here. So then the thing is that first of all, right, so you just write this form, right? So in this form here, on the left. Right. So first of all, you try to, right, so write this in this form. Okay. And then you have this component and this component, right? Now this, you call this the capital M, right? So and then you call this the capital N. So that's what I write here. Now you test whether this M is partial V partial X, and whether this N is partial V partial Y. Right. So, but without, right, so at this point we don't know anything about V, right? So, but again, so we just do the derivative, right? So take to test whether partial M partial Y is equal to partial N partial X, right? So test that. Indeed, right? So they are the same. So then we know that, right? So there exists the function V X and Y, okay, such that, right, partial V partial X is this function, and partial V partial Y is this function here. So then what follow, right? So is, as I said, is what happened in chapter 3. Okay, chapter 3, we have the exact same potential function. So from partial V partial X, okay, so if given by this, so then I integrate this equation 1, okay, with respect to X, right? So then I will get V equals, right, so X cubed divided by 3, 1 plus Y cubed, plus some unknown function of Y, okay, plus C. So then I differentiate, okay, so this function V, okay, with respect to Y. So from here, I differentiate with respect to Y, then I got this, okay, X cubed Y squared plus F prime Y. So then this equation here, partial V partial Y, has to be the same as this equation 2 here, right? Because both refer to partial V partial Y. Okay. So equating this 2 and 3, then I got F prime Y equals to just Y squared. Okay. So then you can find F of Y. Right? So after you find F of Y, then you are done, right? So because this V is just this term plus F of Y plus C, right? So in the end, you find that this V is this whole bunch of terms plus again some unknown constant. So then this is the potential function, right? So the function, and then the solution, right? So the solution to this equation, remember, is the contour line, of this V function. Okay. So that means it's just v equals to some constant. Therefore, the solution is this. Okay. So this one equals to some constant c prime. So if you are familiar with how to find the potential function from the conservative field, okay, so these procedures, okay, should not be unfamiliar to you, okay. But if not, okay, so you need to go back to review that part, okay. So now we have done all these four methods, okay. So I would say the first, they are not actually too difficult to memorize, right? Because separation of variable is just putting one variable to one side, the other variable to the other side, right? So the homogeneous equation is actually also separation of variable, right? But before doing separation of variable, you need to do a substitution, okay? So, and the exact differential, right, that I just talked about, right? So it's very closely related to what you learned in chapter 3 also. So next, I'll talk about this one. Okay. So this is specifically for the linear ODE, and the method is called the integrating factor. Integrating factor. So this is the kind of ODE that we are going to deal with. Okay. So first of all, right? So if you look at it, okay, you can also first ask yourself whether you can use the method you have learned, right? So to solve it, right? So and whether you can use separation of variable, right? So how do I look at it? So if I have this equation, then I have this dy dx equals q of x minus p of x y, right? And then because of this the fact that you have this p of x, right? So with this y, but this one does not with a y, then you cannot just simply take out this. You cannot just simply put this y, right, to the left hand side, right? So in this case, right, so in general, of course, it depends. If q of x is just 0, then you can do that. But if q of x is just 0, then you can just, the left hand side become dy divided by y, and then the right hand side just px dx, right? So, but in general, if you have this q of x here, then cannot do that, right? So now in this linear ODE, okay, so there is a method that we'll use. So that method is known as the integrating factor. Okay. So the trick is as follows. Okay, so first of all, okay, we multiply both sides of the equation, okay, by this r of x, okay, a new function, a new unknown function, multiply both sides by this r of x. So and the purpose is that after doing this, okay, so we hope that by carefully choosing the r of x, the left hand side, okay, the left hand side can be written as the derivative of this product r of y. So because from here you can see these two terms sum together, right? So it looks like that you have used product rule, right? So then I hope that this one can indeed be written as this, right? So from looks like a product rule expansion here. So, but if that has to be satisfied, okay, so that means, right, so this term here, which I write here, right, so this term, if I actually use product rule, right, so then I will get this. So that means that these two terms has to be equals to these two terms here, right? So then we compare the two terms on the left hand side and the two terms on the right hand side. Okay, so the first term, this one cancel with this one, right? So but still we have this one and this one, right? So that means for this to be satisfied, so we require, right, so this red term to be equals to this red term here, right? So then now I have a new ODE, okay, for R of x, okay, for R of x. So why do we want to have the ODE, right? So to be written in this form, okay. So because if we can write it in this form, right? So then this equation actually can be solved just by direct integration, right? Because if for this equation, if you integrate both sides, right? So if you integrate both sides, so the left hand side is just, right? So this just undoing this derivative. So the left hand side is R of x y, right? And the right hand side is the integral of this R of x qx dx. Right, so but they are all function of x only, right? So you should be able to do it. Now then you know y is just this integral divided by r. Okay. So therefore, the key of solving this ODE, right? So is finding r, right? Finding this function that you try to multiply, okay, to the both sides. So then to solve for r, then from this condition, we know that we have to solve this new differential equation. Okay, so drx dx equals rx px. So that is, right, so that is dr dx equals r times p of x. Right, so and you can see that this can be done using separation of variable, right? So putting all the terms for r to the left hand side, and then right, so the x term to the right hand side. Okay. So then separation of variable, right? So then you integrate, and then you get this log of absolute value of r equals the integral of p of x. So then that means this r is given by, okay, plus or minus, because of this absolute sign, plus or minus the exponential function of this integral px. So this integral px dx is known as the integrating factor. Okay, it's known as the integrating factor. So you have now you might ask, so what about the plus or minus? Which one should we take, right? So it actually doesn't matter, right? So whether you take this plus or minus, right? So because at the end of the day, you are multiplying this r of x to both sides of the ODE, right? So whether you have this extra minus sign or not, right, doesn't matter, right? So they cancel anyway. And also, when you integrate, right, when you integrate this p of x dx, right, so you get some function. I don't know what function it is, but let's say g of x, right? So but plus some constant, right? So that means your integrating factor, right? So if I have this r of x should be equals to, right, e to the g of x plus c, right? And then does it matter what kind of c we pick? Okay, so and it turns out it also doesn't matter, because this e to the g of x plus c is just e to the c, e to the g of x, right? And this e to the c is just some constant, let's say c prime. And again, right, the same question. Okay, when you find r of x, whether you have this constant factor in front doesn't matter, right? Because at the end, this r of x multiplied to both sides of the equation, whether you have this extra prefactor in front doesn't matter. So therefore, when we look for r of x, we just make it simple, right? So we don't worry about the minus sign, and then we don't worry about the integration constant that we got, right, from this indefinite integral, right? So then we always just say that, okay, r of x is equals to exponential to this of this integral. Okay, you can see that in this integral, it looks funny. I write down upper integration limit, but I don't have this lower integration limit. Okay, so basically, it's just a funny notation to tell you that just do an integral, just do this integral, and then right. So when you do this definite integral, right? So you have this. After doing the integral, you substitute the value for the upper limit minus the value for the lower limit. Right? So, but here I don't have a lower limit, so that means don't worry about that. That means you just integrate it, substitute this upper limit, which I call x. Don't worry about it. Or in other words, that simply means that just integrate it, treating it as an indefinite integral, but don't add the integration constant. Okay, that really what it means. Okay. So and now, as I said, so if this ODE, right, so can be written in this form, right? So and that now that you have found x r of x, then your y is just given by this. Okay. So this is a standard, right? So recipe that you just use, right? So you, as long as you remember the idea that you are trying to multiply, right, this extra function to this ODE, right, such that, right, so the left hand side, right, can be just written as one single derivative, right? So then that's the idea that you want to remember, right? So and the key is that once you get R, you are done, right? And the way that you get R is also standard. Okay, it's also must be this way. Okay. So that means if you just look at this linear ODE, okay, you basically don't need to think too much, right? So you just find R of x first, okay, and R of x is the exponential function of the integrating factor. Right. So this is a simple example, right? So then this is the equation I want to solve, right? So then this is my P of x, and this is my Q of x, right? So this is just so simple, and in fact, this is can be solved with separation of variable already. But here we try the integrating factor, right? So the P of x, right? So actually just a constant, right? But still I call this P of x. Okay. So then this R of x, so remember what it is, right? The exponential of the integral of P of x. So it's just the exponential to the integral of minus 3. Then this is e to the power, okay, minus 3x, right? So then next, right, so you know that you are going to multiply this r, right, so to both sides of your equation, right? And then because of that, right, so then the left-hand side can be written as just this single derivative. And then the right-hand side, right, so you have this 6 multiplied by this r of x. And then that you integrate both sides. And then just only keep y on the left. Then you're done. So another example, okay, so this time is slightly more complicated. Okay, so first of all, always remember the form, right? The form that we are looking for linear ODE, right? So this. Right, because first we look for this form, right? So because we know that the integrating the R of x, right? So it's always this. So then we look at this equation. Okay, so which one is the P? So first of all, we have some extra things up front here, right? So first we'll simplify it, right? So is that I divide both sides of this equation by x squared. So such that I have this form which is more familiar to us, right? So that now that if I look at this one, I recognize what is the P of x, right? The P of x is this. So then the R of x is the integral of this P of x. So the integral of this minus 2 divided by x. Okay. And then you have this log function up here, but you have this exponential here, right? So just you end up just getting 1 divided by x squared. So well, you don't need to worry about the absolute sign here anymore because you have the square. So then, right? So then next, right? So I multiplied the both sides of this equation by this 1 over x squared. Okay. And then you'll see that for the left-hand side, right? So it's just given by this derivative of this whole thing, right? And then on the right-hand side, just 1 divided by x cubed, right, times this 1 divided by x squared. Okay. And then again, integrate both sides, and then only keep y on the left-hand side. Okay. So then this is the answer here. So again, this is a very standard method, right? So just do a couple times, so I believe you will be able to memorize. So how it works, right? So write the equation in this form, right? So look for P, and then do the integral, right, in order to find R, and then multiply the R to both sides of the equation, right? So and then you know that the left-hand side can be written as just one derivative for the whole thing, right? And then integrate both sides. So this is the standard method here. So okay, so next there are a couple more things that I'll talk about, but I don't want to do it today. I want to actually have you to work on another a tutorial problem. Okay, I want you to work on another tutorial problem, which is question 3. Okay. Well, yeah, but actually, let me see. Okay, before letting you do question 3, I need to mention one more thing first, because that's related to this slide here. Okay, is that I do believe that you have learned about the radioactive decay, right? So well, I'm not going to talk about really the physics, but here it's just that you make, if you have a large number n, right? So many undecayed atoms, right? So you know that you will lose, the n will decrease as a function of time, right? So that decrease this dNdt, so that the rate of change of this n, okay, is given by, is proportional to the number of undecayed atoms at that time, right? So that's the radioactive decay, right? So it's modeled by this first order ODE. Okay, so first of all, I believe you have heard about this before, right? So okay, so that's good, right? So in this case, so we just have undecayed to decay, and that's the end, right? So for this equation, okay, so I do also believe that I don't need to talk about much, because this is just separation of variable, right? So separation of variable, you will be able to find out the n as a function of time is given by some constant times the exponential decay function, right? So and the constant up front, right? So really depends on the n you have at t equals 0, right? So or t equals t naught. Okay, so but this unknown constant, right? So can be solved only when you tell me the so-called initial condition. So this is the background that I believe that you are already familiar with. So here in the tutorial problem, so I give you a slightly more complicated situation, is that it is a radioactive series. Okay, so basically, you could imagine initially we have all the undecayed atom X. Okay, so and then over time, okay, it will decay to another element Y. Okay. However, this Y is also not stable yet. Okay, it will also further decay to the Z. So that's the final product, which is stable. Okay, so this I'm considering this decay series. Okay, so then we are going to use the differential equations to model this process. Okay, so I want you to look at this question and try to do that. So just try to do the part A and part B first. Okay. Part A and part B. Okay, so first consider part A. Okay, so part A is to look for the decay of this x, right? So part A should be straightforward because although, right, so after x is decayed to y, right, so y also decays to z. So but when I ask you about the decay of x, right, so we don't care about what happened after that, right? So then we just simply just write down dx dt is equals to minus, okay, the sum rate times x itself. So the rate, right, so will be given by the question, right? So the rate, right? So this is actually just x itself. So just one x. Okay. So well, I should call this one. Okay, so the whole thing is the rate, right? So but the factor in front, right? The factor in front is called the decay constant, right? So but anyway, the whole thing, right? So just minus 1x. Okay. So because it's given in the question, right? So the decay rate just x itself. Okay. So now we just solve this. Okay, I'll just write down the answer, right? So the x as a function of t is just some constant a e to the minus t. Right. So this is what we have for part A, right? So but of course what is A is at this point, right? So it's an unknown constant, right? But with the initial condition given, right? So we can figure out A, right? So it says that at t equals 0, x is given by this capital N, right? So that means at t equals 0, right? So then we have this capital N, right? So equals to A, right? So e to the minus 0. So this A is equals to N, right? So that means, right? So the final answer is that right? So x is N e to the minus t. So that's part A, right? So now part B. So now we want to talk about the rate of change of y. So this one is more complicated because there are two processes happening together. First of all, right? So because as a function of time, x is decaying, so that's why y is increasing, right? So however, y itself is unstable also, so then y is decreasing. So that is so dy dt will have the two contributions, right? So one is an increasing, so which is due to the decay of x, right? The other is that it's decreasing due to decay to the z. Okay. So that's why. So this dy dt, first of all, is given by, right, the contribution from x. Right, the contribution from x is give you the increase. It's actually given by this term x. Okay. And the other process, right? So which is making it to decrease is the decay of itself, right? So the decay rate for this y okay, is 2y. So that's why I have this minus 2y. Right? So x, right? So because of the fact that this x is decaying, right? Minus 2y is because the y itself is decaying. So that's why this is the differential equation that we have. Okay. So now the good thing is that we know x, right? From part A, we know x. So then let me write dy dt plus 2y. So equals x, right? And x is just this. Right, so then that would be n times e to the minus t. So this equation will use integrating factor, okay, to solve it. So instead of dy dx, right? So we have dy dt here, right? So, but we call that. So we are going to find the r of x, okay, the r of x. So again, right? So recognize the terms that we need, right? So the r, well, not r of x this time, but r of t. So the r of t that we are looking for is the exponential of integral of just 2. This one. So which is just e to the 2t. So what next? Then we multiply, right? So r of t, right? So r of t, r of t. So then the right hand side, you find that it's just n e to the t, right? And now, what about the left hand side? The left hand side, okay, so we find that this is right, so e to the 2t dy dt plus e to the 2t times 2 y. Right. So then the left hand side, you can see that this is just e dt y times e to the 2t. And that gives right hand side e to the t. Then do you know how to solve it, right? So now at this point, right, so you are just going to integrate both sides, right? Integrate both sides. And then you can solve for y, right? So, and we will don't have time to finish all part C and D here, but you can see that part C is asking you to find out the dz dt, right? The dz dt. And dz dt, how do you get the dz dt? You just consider the rate of decay of y, right? So because whatever decay from y will give you the z. right? So from there, you can find that. Okay, so this point, I think I want to stop here for today. Okay. Yes.